My gratitude to the organizers for giving me this opportunity. The title of the talk is on two-dimensional compact real hypersurfaces of a complex space form. Sorry, table of contents won't appear. I will divide my talk into 5 parts. First, we prepare some notations, basic formulas and definitions for hypersurfaces of a complex space form. Next, I will introduce some results for hypersurfaces in two-dimensional complex space form. And section 3 is main part. I proved our main theorem. And in section 4 and section 5 are my current interest. Section 3 and section 4, we treat rich tensor of hypersurfaces. First, we prepare some definitions and basic formulas. The definition of complex space form. M denotes the Keralian manifold and D its Riemannian metric, and J the complex structure. That is, it satisfies this condition. For each plane P in the tangent space, the sectional curvature Kp is defined by this equation, where large x and y is the orthonormal basis for the plane. And if P is invariant by J, then Kp is called homomorphic sectional curvature by P. And if the homomorphic sectional curvature is constant for all J invariant plane P, then the Keralian manifold M is called complex space form. For example, when the homomorphic sectional curvature is plus, then it is complex projective space. If C is equal to -4, then it is complex hyperbolic space. We denote complex space form of complex dimension n of 4 times C holomorphic sectional curvature M and C, and its complex structure J, the Hermitian Keralian metric, the operator of covariant differentiation. This is the ambient manifold in this talk. And let M denote the real 2n-1 dimensional hypersurface and its induced metric G, induced connection nabla, and N denotes the unit normal vector field. Then we have the Gauss and Weingarten formulas. Differentiating tangential vector field y by x in ambient manifold, and taking a tangential part and normal part. This is an induced connection, and this 1,1 tensor is called shape operator. This shape operator also appears in second equation. Here, n is the unit normal vector field. Next, we give an almost contact metric structure on hypersurface. We define 1,1 tensor phi and eta and z by this equation. Taking a tangential part of Jx, we define phi x, and taking a normal part, we have eta x. And this z is called structure vector field of real hypersurface, defined by minus Jn. N is a unit normal vector field. Then this item satisfies the following equations, and it is an almost contact metric structure on real hypersurface M. Besides, we have these equations with respect to the differentiation of z and phi. And the Riemannian curvature tensor field with respect to the induced connection R satisfies this equation of Gauss. And the differentiation of shape operator A satisfies this equation. Here, this derivative means in the previous page, we used this. It's and taking a trace of the Riemannian curvature tensor field, we have the Rich tensor, and we denote it the item S. Sometimes Rich tensor are considered 2-0 tensor, but in this talk we use 1,1 tensor S. And trace A means the trace of the shape operator. When the structure vector field z is a principal curvature vector field, that is, for some function alpha, the shape operator A satisfies A z is equal to alpha z, then we call M a Hopf hypersurface. And if the hypersurface satisfies Hopf condition, then we have this proposition. We use this to prove our main theorem. For tangent vector field x orthogonal to z, if it is principal curvature vector field, then it satisfies this equation. And this is an example which is not a Hopf hypersurface. It is called ruled real hypersurface. For a real hypersurface of a complex space form, we define a distribution T0 by this equation at each point small x in M. It is a tangential vector orthogonal to the structure vector field. If this T0, distribution T0 is integrable, and its integral manifold is a totally geodesic submanifold of n-1 dimensional complex space form, then the real hypersurface is called a ruled real hypersurface, which is not a Hopf hypersurface, and we remark that it is not compact. We use it later. The study of hypersurface in two-dimensional complex space form has many difficulties. Yeah. n-1.
This integral manifold is what's the dimension of this integral manifold? What's the dimension of the integral manifold?
This one?
No,
This
the
one?
integral manifold.
That one?
Itself,
Yeah.
The whole thing,
The study of hypersurfaces in two-dimensional complex space form has some difficulties. So many results for hypersurface is given under the condition that the ambient space is Cpn, n is greater than or equal to 3. In this talk, we mainly treat hypersurfaces in M2C. These are the early results. First, any connected real hypersurface in two-dimensional complex projective space with three distinct constant principal curvatures, that is the eigenvalue of the hyperoperator, is congruent to an open set of a tube of the complex quadric. And next, Professor Bent and Professor Diaz-Ramos gave the theorem for constant principal curvatures. Let M be a connected real hypersurfaces in the complex hyperbolic space CH2. Then M has constant principal curvatures if and only if it is an open part of a homogeneous hypersurface in CH2. That is, M is an open part of one of the following: a geodesic hypersphere, a Hall sphere, a tube around a totally geodesic CH1 or RH2, or a ruled minimal real hypersurface, or one of its equidistant hypersurfaces. And I don't use this theorem to prove our main theorem, but I think it's very interesting. The condition pseudo-Einstein is defined as this equation. If the Ricci tensor satisfies this condition, it is weaker than the condition Einstein for functions a and b, then it is called pseudo-Einstein. Recently, the pseudo-Einstein real hypersurface in CP2 and CH2 has been classified. It is locally homomorphically congruent to one of the following hypersurfaces: geodesic hypersphere, Hall sphere, a tube of totally geodesic, or a non-homogeneous tube of a certain homomorphic curve in CP2, or a Hopf hypersurface with xz is equal to 0, which are constructed by a pair of Legendre curves in the 3-unit sphere. Now we move to the main part of this talk. Condition that S g is equal to beta g. S is a rich tensor of type 1,1 and g is a structure vector field. And this condition is weaker than the condition A g is equal to alpha g, which is a definition of Hopf hypersurface. If the real hypersurface is Hopf, then it satisfies this condition. We consider this condition for hypersurfaces in two-dimensional complex space form. First, we prepare a lemma. Let M be a real hypersurface in M2C and C not equal 0. If the rich tensor S satisfies S g is beta g, beta being a function, then M satisfies one of the following. M is a Hopf hypersurface, or when M is not Hopf, there exists a vector x tangent to M that satisfies a vector field x tangent to M that satisfies ax equals 0 and eta x equals 0. Or M is a ruled hypersurface. We remark that in this section, we consider local case only. The proof of the lemma. Suppose S g is equal to beta g. Then we can prove that taking a suitable orthonormal frame, we can locally express the shape operator A as this matrix. Here we have put Hi is GAEI g and alpha is equal to A g g. Then we have this equation obtained by the equation of Gauss. Using this and previous matrix, we have these equations. So by the straightforward computation, A satisfies one of the following. H1, when H1 is not equal to 2 is also not equal to 0, then shape operator vanishes on the homomorphic distribution T0, and it is integrable, and integral manifold is totally geodesic. Then we see that the real hypersurface is locally congruent to a ruled real hypersurface. Or otherwise, we have if H1 is not equal to 0 and H2 equals 0, then we have AE2 is equal to 0. Next, to prove our theorem, we compute differentiations of each vector field of orthonormal basis. Let M be a real hypersurface in M2C. If AE is equal to 0, A1 not equal to 0, and H1 not equal to 0, here these items are this one. Then we have these equations. And this gamma and lambda satisfies the following equation. We can prove these equations using the equation of Kodachi by the straightforward computation. And using these lemmas, we can prove our main theorem. Let M be a compact real hypersurface in M2C if the Rich tensor satisfies S g is equal to beta g, where B being a function, then M is a Hopf hypersurface. Suppose M is a compact non-Hopf hypersurface, and if S g is equal to beta g, then our previous lemma implies that the shape operator satisfies this condition. And we use this formula for Rich tensor. For any vector field X on Riemannian manifold, we generally have this formula. Divergence of X and the Rich tensor. Using lemma 3-2, which is a derivative of orthonormal vector fields, we have these equations. And using this equation given by lemma 3-2, we have this equation. Here, 3 times C is a constant. When the ambient manifold is complex projective space, then we suppose C is equal to 1, and if the ambient manifold is complex hyperbolic space, then C is equal to -1. Then the left-hand side is 3 or -3. Then we suppose that M is compact. Then from this equation, we see that this is a contradiction. Taking one integral, the right-hand side vanishes, and the left-hand side doesn't vanish. Using our main theorem, we have some classification theorems. Suppose M is Hopf hypersurface, and this beta is constant. Then we can classify hypersurface which satisfies S g is equal to beta g. When M is Hopf, then it is locally congruent to a geodesic hypersphere or a tube around the complex quadric. And if M is a Hopf hypersurface in complex hyperbolic space, then it is locally congruent to one of the following: a geodesic hypersphere, a holosphere, a tube around a totally geodesic CH1, or a tube around a totally geodesic RH2. Next, if M is compact and beta being a constant, then M is locally congruent to one of the following: when the ambient manifold is complex projective space, then M is an open part of a geodesic hypersphere or a tube around the complex quadric. If M is a Hopf sorry, this is mistake. If M is a hypersurface in CH2, then it is locally congruent to one of them.
What's the difference between this theorem and the previous one?
In this theorem 3-4, we assume that M is a Hopf hypersurface. And in this theorem, we suppose M is compact.
The conclusions are same. Same conclusion.
Yes.
Different. Same conclusion.
Sorry, I forgot precisely. Probably the same.
But the hypersurfaces into B, C, and D are not compact. There's only 2A is compact.
I see. I will check again. So, in the next section, this is my current interest and joint work with Professor Inoguchi. If the curvature tensor field R and the Ritz tensor satisfy this condition, we call S the pseudo eta parallel Ritz tensor, which is related to the early result. In 1989, Professor Kimura and Professor Maeda showed that if the curvature tensor and Ritz tensor satisfies this condition, then there are no hypersurface which satisfies this kind of condition. And Professor Ki, Professor Nakagawa, and Professor So classified hypersurfaces which satisfies this condition. And this condition is closely related to first condition, and it is a bit weaker. In this condition, X, Y, Z, and W is orthogonal to Z. So it is weaker. And this condition is related, but in this condition, X, Y, Z, W is orthogonal to Z. For the condition, we proved this theorem, but we have to suppose n is greater than or equal to 3. Let M be a real hypersurface of a complex space form M and C. C is not equal to 0 and n is greater than or equal to 3. Then S is pseudo eta parallel if and only if it is pseudo Einstein. If M is a hypersurface in complex projective space, then M is locally congruent to a geodesic hypersphere or a minimal tube of radius pi over 4 over complex projective space Cp n-1 by 2 with principal curvatures 1, -1, and 0. Whose multiplicities are n-1, n-1, and 1 respectively. When the ambient manifold is CHN, then M is locally congruent to a geodesic hypersphere or a tube over a complex hyperbolic hyperplane or a whole sphere. But when the ambient manifold is a complex space form of complex dimension 2, Professor Cho, Professor Hamada, and Professor Inoguchi gave a result when the hypersurface is hop. The hop hypersurface in CP2 or CH2 with pseudo-parallel Lichten operator are locally homomorphically congruent to one of the following: a holosphere, a geodesic sphere, a homogeneous tube over CH1, or a non-homogeneous real hypersurface which is realized as a tube over a certain polymorphic curve in CP2, or a hypersurface, hop hypersurface with eggs is equal to 0. And by the straightforward computation, we can easily see that a ruled real hypersurface M in M2C does not have pseudo-parallel Ricci operator. Ruled real hypersurface is an example which is not a hop hypersurface. But not yet, we don't have result for whole real hypersurface in two-dimensional complex space form. Are there any non-hop hypersurface of M2C that satisfies our conditions? This is my next problem. And talking about the examples of non-hop hypersurface of M2C, recently very interesting examples are given by Professor Ibe and Professor Ryan. So I will give an introduction of the example finally. Example of the non-hop hypersurface of M2C. First, I give some definitions. Let I be an open interval in R and gamma the regular unit speed curve. It is called regular framed curve if there exists a unitary frame TJT NJN defined along gamma which satisfies these conditions. Here, this prime means covariant derivative with respect to gamma prime along gamma. And K0 is called a holomorphic curvature, K1 the transverse curvature, and tau the torsion, respectively, of gamma. The example has this type of shape operator. If this beta vanishes, then A satisfies the hop condition. HP is a subset of TPM, the smallest subspace that contains GZ, the structure vector field, and it is supposed to invariant under the shape operator A. When H is a smooth two-dimensional distribution on M, we can locally construct an adapted orthonormal frame GZ X phi X. With respect to this orthonormal frame, the shape operator can be represented by this matrix form. In this case, H is spanned by the structure vector field GZ and X at each point. And this one is a principal vector. This is a construction of the example. Let alpha t, beta t, lambda t be analytic functions on an open interval I satisfying the underdetermined equations system them with beta t nowhere there. Let gamma t be a unit speed analytic framed curve in M2C defined for t in I, with transverse curvature nu t and zero homomorphic curvature and zero torsion. Then there exists a non-Hopf hypersurface M such that the distribution net is rank 2 and integrable. And M has a globally defined frame xz, phi x, with respect to which the shape operator has a form star. That is, the shape operator can be represented by this form. And alpha, beta, lambda, and nu are constant along the ribs of H. And M contains gamma as a principal curve to which the vector field y is tangent, and along which the components of A restricted to coincide with the given solution of the ODE system. I think this example is very interesting because this matrix always appears when I compute the hypersurface. Sometimes we can take orthonormal basis and when I study real hypersurface, this type of shape operator frequently appears. And so I guess that this type of example exists, which is not Hopf. But I don't know the construction yet. In two-dimensional case, this example is obtained, so I want to check that whether this kind of example satisfies our condition. For example, this one, and pseudo eta parallel, and so on. This is my next problem. Thank you.